All right. So I think I wanted to. So one of the things that I wanted to try to do today is actually get a little closer, because I realized I maybe spent a bit too much time understanding the whole thing with blocks, but I just now realized that maybe we have a chance at getting to a solution faster, because it's not so much about building a specific representation of G over K, but maybe it's easier than I think, because it says let K be a large enough field with characteristic 2. So let's go back to these. And I'm going to do two things. I'm going to have grok for like deeper text, and I'm going to have the voice here. But I'll be muting the voice from time to time, because it's not good at like shutting up, right? So I cannot just leave it on. Anyway, hey,
Yeah.
yeah, thanks. So, look, I wanted to kind of go back to the thing that I was doing with the group theory problem the other day, and I want to understand if you can give me a very, very high level of what the characteristic of a field is. I believe, if I recall well from previous sessions, that a field of characteristic 2 is actually a field with 2 dimensions. Could it be like a two dimensions vector space? Can you correct me or confirm that?
Oh, all right. So you mean the characteristic of a field. It's actually just the smallest positive integer, p, where p times 1 equals 0 in the field. For example, in characteristic 2, 1 plus 1 equals 0. But that doesn't make it a two-dimensional vector space? That's mixing up two ideas. The characteristic tells us about the field's arithmetic, not its size as a vector space. Want me to explain it with an example?
Yes, please.
All right, let's take a peek at this. Picture a tiny field like real number 2, the field with just two elements, 0 and 1. Adding them, 1 plus 1 equals 0. That's why its characteristic is 2 add 1 to itself twice, and you're back to 0. Now, think of it as a vector space over itself. It's one-dimensional.
Okay,
Just
wait,
0.
stop there. I don't think that's the right use of the time right now. Okay, so it's something that is telling us a structure around the sum operation.
Yep, you've nailed the core. The characteristic ties into the sum operation, showing how adding the number 1 repeatedly works.
Okay, and does it have a meaning if you say that that you're looking for a field that is large enough, but with characteristic 2? It almost feels like a characteristic 2 field is still small. But maybe you're right. Maybe it's not about, because there could be multiple elements that
Exactly. You're getting it. Saying a field is large enough, but has characteristic 2, means it has elements where adding 1 twice gets you 0, like 1 plus 1 equals 0. But the field itself can be huge.
Yeah.
For example, real number 2, fields with 2 nanny elements, are characteristic 2, but can be massive for big N.
So
It's not
okay. So now let me see, how can I relate that with like can I use the fact that I know that a field has characteristic 2 in a way that it helps me in finding how many blocks an algebra KG would have. I know G, like let's imagine I know the structure of G, right? And I know that to find the blocks, it's about it's a starting point would be to basically get representations of G over that field, right? But does the characteristic tell me something? Because I can't really connect the two, right? In a way, I understand. Yes, wait a second. I understand that the concept of, yes, the concept of the blocks is that when you're operating within the elements of KG, that you're basically staying, so these are the blocks where you're staying within that subspace, right? So if we're saying that it's a field with characteristic 2, it's telling us probably something, right? Because it's telling us that if there's an element such that this element plus 1 equals 0, does this tell us something? Is that one of those idempotent things that we're talking about?
exactly. You're circling the right idea. Characteristic 2 changes how things behave in KG. Blocks are indecombinable, two-sided ideals in the group algebra, tied to how representations split. Since 1 plus 1 equals 0 in characteristic 2, it simplifies things like the two-silo subgroup structure or idempotence. For instance, in char 2, Elements like g plus 1 for g and g often have 1g plus 1 times 2g and g squared plus 2g plus 1. But since 2 is 0, that can collapse nicely. This helps count blocks by grouping representations differently than in odd characteristics. Does that spark a connection for you?
Yes, that actually helps. Yes, so that's gonna help us count. It's gonna help us count the blocks. It's gonna probably make it easier to count the blocks because of what you're saying, because we can probably come up with different representations, but we will basically see that a lot of them just collapse to being the same, because you're saying that a field of characteristic 2 is a field such that has that property that there is at least one element. We can call that, I guess we can call that element just A, right? It doesn't have to be 1. Like it can just be like A plus A equals 0.
Yeah, you're on the right track. It's not quite that there's an element A where A plus A equals 0. It's that every element satisfies that.
Every element satisfies that. Every element in the field satisfies that. Adding it to itself is 0.
Right. So in a field of characteristic 2, adding any element to itself gives 0, because 2 equals 0. That makes life weirdly simple for counting blocks in kg. Things like g plus 1 times 2 collapse to just g squared plus 1. Cutting down on distinct representations, it shrinks the possibilities.
Thank you. That actually makes sense. Okay,
Awesome.
thanks. I'll pause for a second. Well, I will not pause, but I'll just mute myself. Stay there on hold, okay? Okay, so now I muted it, so it cannot talk. Let's see if it actually is able to stay silent. I'll do, again, as I said, I can't do a lot. I just really I can only do like a few minutes. But I just wanted to kind of get that out of my head, because it just crossed my mind this morning. I just can't get out of that. I wanted to get that out of my head. So the characteristic is telling us that every element added up to itself. Okay, so now let's think about, like, let's go back and think about G. The thing is, I kind of forgot. I kind of forgot everything about G at this point. And I know we had G. I know we had G. Let me see if I can go to the projects, and I can ask it here. Can you dig out the SymPy code that was calculating G? Should be able to find it, right? You can. Come on, G. Really, you're telling me that you're not like okay, guys. Give me a second. All right. I'll probably I'll stick the videos. Anyway, you're telling me that you can't remember that. This was before all that. Oh, maybe I actually ended up doing this outside of the workspace. Fuck. Oh boy. No, there. I think there was the file somewhere here. Quotient theory group. I'll see if I can actually generate it again. Give me pi code. So let's take these and copy, and I'm gonna ask it to generate SymPy code that computes the group G as per the following definition. I believe it did actually quite well just with that. All right, so let's go while I'm waiting for something. Let's go back to the following question. If I'm trying to now approach the finding representations of a group over a field, what's the best way to do that? Can I do that with a tool, or is there a tool out there that helps me do that, like SymPy?
SymPy is not really built for full group representation theory, but you can use it for smaller groups to compute character tables or basic rep stuff. For serious work, try GAP or SageMath. They're powerhouse tools. Want tips on using one of them?
No, thank you. How would you approach this manually though? Is it approachable to say I have that, like, let's say I have a group G, and I know group G's elements roughly. It's not too big of a group, probably like 108 elements, if I recall well. And then 100 elements is actually big. How would you approach looking for the blocks, looking for the representations of that group over a field of characteristic 2?
Start by figuring out if the group structure helps, like, is it abelian or not? If it's not too complex, write down its conjugate classes and use Burnside's lemma or Maschke's theorem to get the irreducible reps. In characteristic 2, focus on odd-order silo subgroups, since even ones collapse. For blocks, look at the block idempotence or decomposition matrices. They tell you how modules split. Want me to walk through a small example with a simpler group?
Yes, please.
Let's say we take the Klein 4 group, V4 equals 1, A, B, A, M, with each element squaring to 1. Over characteristic 2, adding any element to itself is 0. Now, build the regular representation, each basis vector EG for G and G. But in char 2, A plus A equals 0, so many things simplify. The rep decomposes into 4 one-dimensional modules, since it's abelian and small. Blocks, just 2. The trivial and the sum of others, as idempotents collapse. Want to try scaling this up?
No, actually, I'd like to peel that off a little bit, because I think you've gone a little too fast. So okay, so the Klein group, so you have the Klein group, which is with elements squaring to 1. Adding an element to itself is 0. Now build a regular representation. Each basis vector EG for G in G. But then E, I guess, is in that field. So many things. Simply the rep decomposes into 4 one-dimensional modules. Why? Is it because of the 4 elements of V4?
Exactly. It's because it's abelian. Every abelian group has representations that split into one-dimensional pieces over any field.
Okay, stop. Let's expand on that. An abelian group is a group where all the elements commute, right?
Right. So abelian means everything commutes, making the rep theory way simpler.
But why? Why? So if all the elements compute, why do the representations split in 4 modules? And what is a module in that context?
They commute, so the group algebra KG can be written as K plus K plus K plus K, 4 copies of the field. Each copy gives one-dimensional module, just a vector where a group element multiplies it by a root of unity, or scalar. So, 4 elements, 4 independent ways it can act, 4 modules. A module here's just a vector space where G acts linearly. Want to see how these look explicitly?
Yes, please. Give me a concrete example.
All right, picture this. Take Klein 4 group, V4 equals 1, A, B, A, M, with A2 equals B2 divided by 1, and AB equals BA. It's abelian, so every element commutes. For a representation, imagine a one-dimensional space, just numbers, say YMR, and define how group elements act. The trivial rep, every G in V4 maps to multiplication by 1. Another, A acts as -1, B as -1, AB as 1. Third, A maps to 1, B to -1, AB to -1. Last, A maps to -1, B to 1, AB to -1. Each gives a homomorphism from G to K dex, the field, non-zero elements. In char 2, scalars. Things simplify. Want to see explicitly? Want to see the matrices?
Wait. So when you're saying like here A maps to like the elements map to 1 -1, like so this was why is it so? Because I understood that the representations, the reps, it was about basically taking the group and then basically turning each of the elements into like a transformation matrix, right? But why are you using ones and -1s in this case?
Because in this simple one-dimensional case, transformations are just multiplications by numbers. In a vector space that's one-dimensional, like
Oh,
MRR,
right. Okay,
or your
okay. I get it. So it's because of it's over a space, it's over a one-dimensional space. So it's just plus. So it's just basically you only can go left or right.
Yeah, exactly. In one dimension, all you can do is scale by a number. In reps, we pick scalars, so group relations hold. For Klein 4,
Continue, please.
1. So we need scalars where G2 equals 1 acts as identity. In characteristic not 2, that gives +1. In char 2, it's a bit different. In char 2, -1 equals 1, so you just get multiplication by 1 everywhere. So in char 2, the trivial rep is the only one-dimensional rep. The others vanish. So for Klein group in char 2, reps aren't as rich.
Okay, so let's step. Okay, so if it's a billion, but I think the group I'm dealing with is sadly not a billion. But if it's a billion, I understand. If it's not a billion, what else can we use as a tools to count the blocks? Not the blocks, but yeah, the representations.
For non-abelian groups, step 1 is finding the conjugate classes. Count those, then use them to figure out how many irreducible reps there are.
What are the conjugate classes?
Conjugate classes are sets of elements that get swapped by group actions. Take an element G in G and find all HJHMN1 as H runs through G. If your group has order 108, list the elements and compute each class. For example, in S3, the 6-element symmetric group, you have classes. 1. IDIS, the 3 transpositions, and the 2 3 cycles. How's
I think it's tough.
that?
It's okay. It's okay. I think there's something wrong with you at the moment because you're spitting out a lot of like dots. Maybe it's because of formulas and shit like this on voice mode. It doesn't matter. But okay. That was helpful. I think I moved a little forward. Thank you very much.
You're welcome. Yeah, sometimes the dots creep in. Sorry about that. If you ever want to tackle that group with 108 elements together, just say the word.
All right, thanks. Yeah, and I think that got it wrong. I'll dig out the file. I'll dig out the file and then I'll make the second session. That was a short one, but actually I did feel like I moved a little forward. At least we know that this statement, characteristic 2, is going to help us with counting the blocks. So something for something. Something for something.